All right, let's get started. Thank you very much for being here. How did you enjoy the conference so far? The conference organizers have done a wonderful job. They make it look very simple, isn't it? But it is a lot of work. It takes enormous amount of effort, coordination. And that is kind of, I use the word simple, I kind of want to lead into it. So we're going to talk about simplicity. And I want to kind of reflect back on what I have been doing for the past several years. And I started out as a programmer a few decades ago. And if you ask me what I have done over the past, let's say, 5-6 years, I have to say that I have deleted more code than written more code in the past about 6 years. And the reason is that I work with a number of clients, number of companies, and when I go in, what I find a lot of times is complexity. And complexity comes in two flavors. One is accidental complexity, and the other is inherent complexity. Inherent complexity is something we cannot easily get rid of. Probably cannot get rid of. But accidental complexity is something we definitely have to remove. But why? Because accidental complexity costs a lot of money to develop software. It becomes very hard to maintain systems. So over the years, the only thing I fear today is complexity more than anything else. And I work really hard to remove complexity and avoid it where possible. So I want to talk about simplicity, but I want to call it as an art of simplicity because I don't think you can just sit there and define it very easily. It is something that you have to kind of work towards. So I'm going to talk about a number of things here, but I was thinking about what are the things that we can look at, and I cannot think of something more complex than several of which we have in this room, several human brains. And each of us carry with us something enormously complex. But rather than calling it as complex alone, I'm really hoping we are carrying something that's very capable. And those two are not the same all the time. Some things are complex and pretty useless. Some people's brain is like that too. But a lot of other people around us are not only complex but very capable as well. And I'm hoping that we can identify capability. And of course, human brain is one of the most complex and most capable. What a well-crafted system. But as capable and as talented as we are as human beings, we don't make good judgments all the time. It's very hard to know how we innovate things. How do we create things? How do we, you look at somebody and say, that's pretty cool, but how did you arrive at that? And they usually don't have an answer. They say, well, I just thought of that. But how do you think of something brilliant like this, right? We keep asking people like this. And when you look at the human mind, it's one of the most complex systems, but yet, as capable as we are as human beings, a lot of things cloud our decisions. A lot of things cloud our decisions making and our ability to think. One of that, of course, is emotion. And the minute we bring emotions, we don't think logically anymore, right? We operate with emotion rather than logic, and that happens as well quite a bit. But if you think about complexity, this reminds me of something that I've read before. This is about, this gentleman over here is Schrodinger. And Schrodinger's cat is one of my favorite. A lot of times I would be sitting at home and talking about something, and my children would say, Dad, that's like Schrodinger's cat. So it's a very common vocabulary in my house to talk about Schrodinger's cat. In 1935, Schrodinger wanted to prove about an experiment. And so he hypothesizes, or he thinks about this experiment where there is a box which you cannot see through, and within this box, there is a little device that will explode and send out some very bad chemicals, and there's a cat inside this box. Now, you cannot open this box because by opening this box, you would have this device explode and it'll kill the cat. So at any given time, is the cat alive or dead? And he argues that at any given time, the cat is both alive and dead at the same time. Now, how is it possible, right? So this can be fairly confusing to think about these things. How could be something both dead and alive at the same time? Now, it turns out that simplicity and complexity are things we deal with every day, but Confucius says, life is really simple, but we insist on making it complicated. Now, there are some people you will talk to. They will take simple things and make it complex. And there are other people who take complex things and make it even more complicated. But it really takes effort to make things simple. But why are things not simple? Why don't we make things simple? Well, there's a sad truth to this. We feel good about making things complex. Would you agree? You go to your colleague and you say, here's my design. And your colleague looks at it and says, oh, this design, yeah, that's simple. And you say, what do you mean it's simple? I worked really hard yesterday doing this. Give it back to me. I'll come back tomorrow. And you go back the next day and you say, I took a little bit while to create it. You better take some more time to understand it. We feel good about creating things complex. And your colleague is looking at it, scratching his or her head, and you beam with pride. It's like, yeah, it takes some more time to understand it. By the way, there is another reason why we like to make things simple. We feel smart when we create complex things. If you create something simple, you're worried that other people will not value what you do. You create something very complex, your coworker looks at it and says, what does it do? And you're like, can you figure it out? And now your coworker takes your code home, spends the rest of the night looking at your code. At 2 in the morning, a light bulb goes in his head, and immediately he tweets it and SMS or calls you and says, I got it. But you got to remember what this colleague of yours is going to do at 2 in the morning. Sits back and says, that was very complex, but for my turn I have to create something even more complex now, right? To impress you the next day. There is another reason why we make things complex. Creating things complex gives us job security. The boss says, no matter what you do, don't touch John because we have no clue what he's working on. So we got to keep him around, right? So that's job security if you create something complex. And there is another problem with complexity, though, with all these said. Have you ever had a chance to eat donuts? Yeah? What happened after you ate one donut? The last time I tried it, I resisted, by the way. No, I'm not going to have the donut. And the minute I tasted the first donut, the next thing I know, I was pipelining donuts. Complexity is like that. You create something complex today, you're going to come back with vengeance tomorrow because it's got to be even more complex, right? So complexity kind of breeds complexity, and pretty soon it's very difficult to see this. Now, Ken Beck coined the term code smell. I love this term, by the way. The code smell is such a wonderful metaphor. Why is that such a great metaphor? Well, what is a smell? A smell is a sense. But code smell is a sense too, but it's very dangerous sense. You walk into a room, and as you walk in, you twinge your nose and say, what's that funny smell? And everybody in the room working away looks at it and says, huh? We don't see anything. We don't feel anything. And then you sit down and you start working. About 10 minutes goes by, you don't feel a thing. Somebody else walks into the room and says, what's that funny smell? And you join the rest of them now. What smell? You get used to this so much, right? And so complexity is like that. You kind of get into complex mode, and you don't even feel that this is complex anymore. You're kind of drawn into it. That becomes a lot of problem as well. So what do? I talked about why these things become complex over time. But Einstein says, any intelligent fool can make things complex and violent. But it takes a touch of genius to really make things simple. And this is actually true. It takes enormously more effort and talent and courage. And courage it is. Because it takes a lot of courage to stand up and say, I am going to make this simple. And I'm not going to give in to pressures of other people ridiculing me because this is simple. And that is, by the way, courage. It takes enormous talent and courage to make things simple. Simplicity doesn't come so easily, by the way. It takes a lot of effort to make things simple. Well, if you are on the bus, and if Mr. Simple was sitting next to you, would you even know that you're sitting next to Simple? Would you say, Mr. Simple, nice seeing you today? So a lot of us don't even know what Simple looks like, because we are being drawn into complexity so much, we don't even know how Simple looks. So it is important to know what Simple is and how it would look like. But it turns out to tell what is simple is a lot of effort. So I kind of went the opposite direction. If I can show you what is not simple, then at least we can avoid that and say, that's not simple, let's not do it, right? So what is not simple? Let's talk about a few examples of what's not simple. Simple is not clever. Anybody here who has written clever code before? Oh, come on, be honest. Absolutely. Those who raised their hand have written clever code and know it. Those who didn't raise their hand have written clever code and are in denial, right? Everybody has written clever code, because as a programmer, you always do. Because you look at it and say, how could I cleverly solve this problem? And when you cleverly solve the problem, what happens? It seems like a brilliant idea when you solve it. You are beaming with pride, and you say, isn't that cool, by the way I solved it? Now think about this for a minute. Let's look at an example. If you are sitting down to write something, I'm sure you've seen people do this, right? Somebody at work writes a piece of code and says X and then does something like this. You write code like this. And you are happy. You're like, isn't that smart? I did something wonderful. And your colleague comes to you and says, what does it do? And you explain what it does. And you say, by the way, this gives you the best performance, by the way. How many times have you heard that? All the time. What performance are you getting out of this, by the way? Oh, it's fast. Faster than what? Faster to solve what problem? I don't know, but it's fast. So we make this extremely fast. And your colleague asks you, what does it really do? And you explain the math behind this. And then your colleague says, but this code looks complex. What about the rest of us in the team? How would we understand? You say, don't worry, I'll fix it. See? No longer it's not a problem. How many times have you seen comments like that? All the time. Very annoying, isn't it? So not only is this code complex, we don't have a clue, and the author insulted us by writing a comment that doesn't help. Right? And now you look at this and say, really? But enlighten me. Why did you shift this? What problem are you solving really here, right? We don't know that. It becomes really hard to understand what's going on with this code like this. So that's very painful, isn't it? So I have written clever code, by the way. Of course, who has not? Everybody has. I've written clever code. And there were times when I would sit there and solve the problem and say, why solve this in this way? Look how much I can solve by using this clever code. It solves 10 other things, and it's extensible, right? Sure, that's awesome. And the last time I wrote clever code, by the way, I was so proud of it. I said, this is wonderful. How effectively not only I solved the problem, now I solved it from recurring again. And 3 weeks later, by the way, my phone rang. It was a support. And I completely messed up in production. Hey, have you seen this problem? Yeah. And in fact, I wrote it. Let me fix it and give you a new release, by the way. And I fixed my code, and I made a release. When things fail in production, the rest of the world sees what mess you made, right? So you fix it. And then I sat back and said, why did this so royally break? And I realized that in my cleverness to solve the problem, I had not thought through a lot of other consequences that may happen. And once I fixed it, I made a very simple solution to fix it. And once I did, I learned a lesson. These days, when I write a piece of code, and as I'm writing it, as I finish it, I think, oh, this is clever. I immediately delete my code, and I start over. Because I know clever code is going to be very costly. For example, what about this code? Public abstract class enum, E extends enum E. Oh, that noise you just heard? That's your brain throwing an exception. This is Enum in Java, by the way. Who understands this code? Not, okay. Let's talk about the 7 o'clock. We'll be here all night long, right? And you start understanding this code. It is so complex. And you think you load everything in your head. And then somebody at work says, what does this do? You start with, well, that usually means that this is not worth explaining. You won't get it. Or that code. Well, here's the question. Programmers come to me and say, excuse me, Venkat, do you have some tools you recommend to obfuscate Java code? Even better, these days they come to me and say, do you have a tool to obfuscate JavaScript code? And I ask them, why do you need a tool? Your programmers write self-obfuscate code naturally. They even don't understand the code they write, leave alone others. Why do you need tools, by the way, right? They're quite fine already. Like this code. What does this code do, by the way? Well, let's start somewhere, can we? What does it do? In square root. Maybe it's an inverse square root. Okay, there's a little clue. Float x. By the way, how cool is that? X. How would you feel if mom and dad gave you a name P? Son, what's your name? P. Is that your middle initial? No, that's my full name, P. How could you have a name called P? That's it. My dad was a programmer. What do you expect? Would you give children a name like P? And somebody complains, oh, P is not, understandable. Okay, L2. How would the children grow up if you give names like that, right? I was teaching a course in Northern Virginia. I was telling this company why you should never use single-letter variables, well, almost never use single-letter variables. One of the guys came to me and he said, do you realize you just came into a software giant company, and you think you got to come and tell us how to write good code? And I said, well, I'm sorry, guys. I didn't mean to offend you guys. If you write wonderful code, just ignore my, advice. It's not wasted if you can just teach other people. Oh, Venkat, I was just pulling your leg. Every variable in our application is single letter. It is code from hell. We cannot maintain it. Oh, you scared me for a minute. I went there 4 months later to teach another course. The same guy came to me and he said, hey, remember last time you came, you taught us not to use single letters? How could I forget? Well, I want you to know, Venkat, you made a big difference. So I was proud. I said, really? He said, yeah, now we use only 2 letters, right? Habits are very hard to break. So by giving a more descriptive name, we can help reduce complexity just a little bit, right? Then what? X half, of course. We understood what X is. Now it is X half, right? And of course, it multiplies 0.5 F times X. Don't ask why, though. Then comes the gem. Star int star ampersand X. What does that do? Well, if that doesn't really help you, what about this? This is beautiful. Of course, we understood very well what it's doing. What about this line here? That's the only thing I have a problem with, if not this. I understand this part. Return X. Thank God we are done whatever we did here. Who's going to maintain this code? I came across another piece of code on the web. Web is a great place to look at code, right? Remember how they tell you your application code should match the application you develop? You got to be very close to the domain. Have you heard those things? Right, your code should match the application. So one guy took this to the heart. He was asked to write a flight simulator. He said, sure, why not? That's it, code for flight simulator. Don't ask me what it does. I'm not smart enough to understand it. I don't want to be on that flight either. Right? So simple code is not clever. Simple is not necessarily familiar. Now, I want you to think about this for a minute. Over the time, somebody shows you something different. And they are crying to you, saying, this is simple. And you're saying, are you crazy? This is not simple. This is complex. But is it? Maybe it is. But is it? So we need to ask ourselves, are you saying what you're looking at is complex? Or are you saying that what you're looking at is not familiar? Because there's a very big difference between the two. If you look at something that's not familiar and you reject it because you're not familiar with it, then you're going to miss out on a lot of wonderful things. If I walk down on the streets over here, a lot of things on the streets are not familiar to me because I don't speak your language. How naive, how stupid it would be of me to complain that everything around me is complex. And I wouldn't benefit from being here, enjoying the place where I am, interacting with wonderful folks like you, right? So what does this say? Anybody knows what this is? Chinese. That's a good sign. First step. Awesome. Anybody else? Japanese. Now we are arguing what language it is. Well, it's a simple, uncomplicated, casual, and common. That's what it says. Now, of course, that is very complex to almost everybody in this room, right? Because we don't know what it is. But the scripts I see is also very complex to me. But is it? No. It is just I'm not familiar with it. There's a very big difference between what I'm not familiar with and what is complex. It is naive of me to complain that something is complex because I'm not familiar with. So I have to ask, is it something I'm not familiar with, or is it something that's very complex? Let's look at an example. I want a total prices discounted by 10%. Anybody has done code like this before? Everybody in this room, right? Absolutely. So let's see how this is going to look like. So here's the prices. I want to total the prices discounted by 10%. So how would I do this? For int price, int I equal to 0, I less than prices dot size, I plus plus. Wait, is it size or length? Size, not length? Would I ever use length? If it's an array. Oh, so I have to know whether prices is array or list. Is it less than or less than or equal to, by the way? Is it less? Are you sure? Have you ever had this off by one error? You write a loop and somebody says, hey, this is broken. Oh, I'm sorry. It's got to be less than 1 or less than or equal to. Isn't it annoying that you have to think about this every time you write? Every time you write this loop, you have to stop and say, did I mess up? No free human in the free world should be subject to that. And if you're doing this to yourself, don't. Right? The world is a better place than this. But why are we writing loop like this still in 2013? No need to, right? Wait till Java 8. Well, yeah. So not better than this, right? Well, let's try this first of all. How would this look like? So double total equal to 0 to begin with. When I'm done with it, I want to print out total is, and what am I going to print? Total, of course, right? Print the value of total. But how would I total in here? Of course, it's very familiar, right? So total plus equals prices dot get value of I times 0.9. So go ahead and run this code and see what it does. Well, it gives us an output 189.0. That's simple, right? Is it simple? It's familiar. I would argue this code is complex. You may say, no, it's not complex. Well, that's because you're in denial. You're so used to it. I had somebody come up to me and say, can you review this code, please? I reviewed the code and said, my dear God, your code is complex. And the person said, I'm really sorry. I don't get it. Why would you tell me my code is complex? Because I'm using something very simple, a simple if statement. I mean, I only have 30 of them here, but it's simple, right? And that's when it occurred to me, oh, they got confused about familiarity and simplicity. They are using if statements. They're very familiar with if statement. So what did they do? They wrote 30 of them together in one function. But when I come to this function, I am like, what are you doing here? Who here thinks writing long methods is a great idea? Raise your hand if you do. Not a single person raised the hand. Who here has seen long methods? Almost everybody. Look at the cognitive dissonance, right? What's the longest method have you seen? Throw me a number. What was that? Notice he doesn't even want to use real numbers anymore. 1.58K. That is what? 1,500 something? Yeah. Anybody else can beat that? Yeah? Go ahead. 2,000 lines of code. I feel like being in an auction now. Yeah, what's your number? 4,000. He doubled your number. Anybody wants to beat that? 12,000. I know. I know nobody in this room writes long methods. The guys writing long methods are at work still, making those methods longer as we speak, right? Because we know better that writing that method is bad. Why is writing a long method not a good thing? Long methods are complex. How is it complex? You start reading, brrr, and then after a few minutes you say, I've read this so far, I've kind of collected those thoughts in my head, and my RAM is becoming full. Now you're not reading, by the way, you're page downing. How much more is there? And slowly you feel a pain on your back. Excuse me, where's coffee around here? Right? And you go get a cup of coffee and you come back and say, do I have to read this explicit, whatever you want to add after that, right? And this is complex, not because of anything else, because you got to load up so much in your head, right? By the way, how can you make this code simple? People would say, well, break it into smaller methods. And somebody would say, no, 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 no. You should not break the method into smaller methods. Why? Because long methods give you better performance. Of course they do. Have you heard people say that? Long methods are faster? No? It works, Sab. They think it works, by the way. Ignore that. Oh, you cannot ignore because they are next to you saying this constantly. So, long methods are faster. You know, they're not wrong. They're kind of right. Long methods were faster. But that's when Nixon was the president. A lot of things have changed since then in the architecture of computers. Compilers have got better. Inlining happens too, right? So the problem is, it is complex because we cannot hold it in our head. It becomes really hard to read it. So this code is familiar, but let's look at line number 9. What's wrong with line 9? It has got too many moving parts. I heard Michael Feather say once, object-oriented programming encapsulates moving part, functional programming eliminates moving parts. The more moving parts you have, the harder it is to understand the code. And more bugs come in. Every time you write this, you got to go and check all these moving parts. Is that in place? It's all tied together. We can do a notch better than this already in Java, right? So we can go back to this code and say, let's say this is int price in prices. And then we can say this is price. Do you feel the fresh air already? A lot of things around it is just gone, isn't it? Run the code, and you can see this code runs through, produces the output also. But I still don't like this code. Why? Because if you look at this code, we all have read about good design, right? Everybody has read about good design. What does good design say? Single responsibility principle. Your code should do one thing and one thing good. What does this code do? Several things. It creates a total variable. It creates a loop. It iterates through the loop. It multiplies the value. Oops, it even throws random boxes. It multiplies the value, as you can see. And then, of course, you total the value together. Look at all the things that happen. Now I come to you and say, I want to change this. What do I want to change it with? Only total prices, only discount prices that are greater than $30. How do you do that? Oh, this is fun. You would come in and say, if price is greater than 30, then total, right? What did we do? We made this code even worse. We increased its responsibility. And if you have code like this, how easy or hard is it to understand this? It is hard. Because every time you got to stop and you got to stare at it. What are you doing? Right? You got to think about this for a few minutes. Let's try this one more time. Just take the simple case where I just want to total the prices after discounting it. So let's go right here. And let's go back and say prices dot stream. This is part of Java 8. What is stream? Well, in Java we're used to iterators, right? We use iterators in Java. Well, stream is an iterator on steroids. It can do wonderful things for you. One of the things it can do for you is to perform an operation called map. So I'm going to say map to a double, given a price value, by the way. And what do I want to do with this price? I want to discount the price by 10%. But what did we do? Notice we removed mutability from code. And you look at that one line, line number 10, what does line number 10 do? It discounts the price. That's it. Single responsibility. What price does it discount? Every price in the collection it discounts. It takes in a collection and gives you a collection. That's why it's called a map operation. Well, great. What's the next thing I want to do? What does the problem say, by the way? What does it say? Total, right? So right there is the code to total the prices after a discount value. Is this code more complex or simple? And for most of us who have only programmed in Java, this code is definitely very unfamiliar, right? Yes, I give it to you. It is unfamiliar for us. But once we get familiar with this, is it simpler than the other code is the question. In the meantime, you are told only total price is greater than 30. How would you do that? You can simply add to the pipeline. You can say dot filter, given a price, only return prices greater than 30. Only pick prices greater than 30, not others. So notice how logically it flows through. And this is unfamiliar, but I'm going to argue this is simple. Not only is it simple to read, simple to write, it is also possible to parallelize this code really easily. By simply replacing the stream with parallel stream, you can run this concurrently across multiple threads as well. So we have to ask ourselves, is a code familiar or is a code complex? And when you look at something different, don't reject it because it's not familiar. Then we lose out a great deal. So is it unfamiliar code or is it a complex code that we are dealing with? That is something for us to ask. So we looked at the traditional way of doing it a little bit better, and of course we put the stream into it. So don't confuse familiar with simple. Simple is not always familiar. I'm sorry, familiar is not always simple. Unfamiliar is definitely not complex. It may be, but not for sure. So we should ask, is it familiar or is it simple? So lots of us are familiar with imperative style of programming. What is imperative style? Where we tell every step of the way what to do. And we also have mutability in code. Functional style of programming is more declarative. You tell what to do and let the underlying libraries figure out how to do it. You expend less effort. You ask for results rather than telling every step of the way what to do. And functional style is more declarative in nature. It costs less to write it. It's easier to understand if done properly, and easier to maintain as well, and easier to extend as well. So a simple code has fewer moving parts. I started out telling you what's not simple, but now we can identify a few things that are simple. A simple code has fewer moving parts. You don't have to do a lot of juggling around, and you just write it, and there are few things that change. Fewer mutability is simple because it results in fewer bugs and easier to maintain, not as expensive. Simple code is not over-engineered. This is one of the problems we have to fight constantly, right? What is the problem in most of what we do? You go to a developer and they say, how do I make this code extensible? Nobody wants to write code that works. They want to write code that's extensible. We're proud. Hey, what did you do? I've gone to companies and they say, oh, we are writing a framework. Why don't you write a product? Why don't you write an application? Who wants to write an application? It's very cool to write frameworks. And I'm scared when I go in. I say, you keep using the word framework, by the way. Why? And they're like happy, proud. Yeah, we write frameworks. When was the last time you guys released the product? Oh, we can wait for that. Well, we're busy creating frameworks. Right? This is over-engineering. Grady Booth said once, first use the code you write, then reuse it. How many people want to write reusable code and end up writing code that's totally unusable? We over-engineer a lot of times. A gentleman named Rube Goldberg got his name by writing a lot of comic strips about complexity. So Rube Goldberg was involved in a comically involved, complicated invention, laboriously contrived to perform a simple operation. In fact, kids around the United States today work on projects, by the way, where the challenge given to them is to create something very complex. And they compete on saying who created more complexity. I went home in one of my trips, and I found a mess in the house, complicated things. And I asked, what is this? And my son said, I'm working on this project for school. What does it do? He said, we don't know quite, but we're trying to figure out, but we're trying to make it more complex. And he came back to me and said, Daddy, can you suggest a way to make this complex? I said, kid, I go around the world helping people to make things simple. And you are asking me to make this complex. Right? We do this naturally all the time to make things complex. In fact, we should be teaching children how to create something simple, not create things that are complex. But we do this all the time. And then we end up creating a complex thing like this, where this guy is inventing a back scratcher. Yeah, you're laughing, but how many times have you seen this in your own code on your projects? Quite often, isn't it? You look at this code and say, what does it do? And the programmer is like beaming with pride. Let me explain it to you. No, don't. I should have understood this already, right? I was working with a programmer once. I saw the code. He took a data from a database, by the way. Yeah, simple action. And then 200 lines later, he created an XML document out of it. I'm like, okay, I understood what you're doing. So I'm following this XML document. It goes to this other function as a parameter. And in that function, 200 lines of code to parse this XML, to put it back into the database. And I'm sitting there scratching my head. Oh dear. So I called him and said, what's this doing? And he's like, isn't that cool? No. Venkat, you don't understand. This is extensible. I said, extensible for what? Well, any service in the world can now send data to this function. And this is completely consumable. It can interact with everything in the world. I said, what is this application supposed to do, by the way? What does it talk to today? Well, all this is in this process. Then why are we doing it? You don't get it. This is extensible. And immediately I picked up my phone and I dialed him. And as he was talking to me, he's like, oh, excuse me, please. Hello? Hey, this is Venkat. What? Why are you calling me? I said, look how extensible this is. I'm never going to talk to you in person anymore. Even if I'm next to you, I'll call you on the phone. I could be moving around. Why would I ever talk to you directly, right? So the point really is, we create, in the name of extensibility, enormous complexity. Who's going to pay for this, by the way? Who's going to maintain it? What was that? The customer. Yeah, sadly. Simple is not terse. So we said simple is not clever. We said simple is not necessarily familiar. We said simple is not over-engineered. Simple is not terse. Some of us have this desire to create concise code. There's a competition among people, right? Hey, look how small my code is. And the next person is, let me show you how you can make it even smaller. And we make it very terse in the process, not concise. There's a difference between terseness and conciseness. Let's take a look at an example. What is this, by the way? I saw this in real code, in real production code. This is from one of my clients. As I was looking through it, what caught my attention was not this. It was what was below this. I'll show it to you in a minute. As soon as I saw it, I said, hey, do you mind? Can I take a photo? And they said, yeah, right, go ahead. And what I saw was this, by the way. These are guys who are very qualified to maintain this application. They have no clue what this code is doing. All these kinds of comments is like message left on a cave, right? Where you're screaming for help. God, please, somebody help me, save me, right? You're stuck over there, not able to get out. Very complex when you have code like this, right? Very difficult to deal with things like this. That's a way to increase complexity because it's hard. Every time you look at it, you got to stare and say, what does this do? What does this mean? Because it means so many things. Let's take a look at this example. I have a test. In this test, I call set price on the top. Then I call max profit. And then I set fail. And then I do a catch. Within the catch, I have an assert true because I hate empty catch blocks. I don't like empty catch blocks. Every time I see an empty catch block, I have to stop and say, why? So I usually put an assert true. My mind is at peace when I see this. But you could look at this and say, oh, this test is verbose. And yes, it is. So what does JUnit do, by the way? An annotation, isn't it? You can say add test expected equals. What a nice way, isn't it? Hey, where did that get that idea from? You see, this JUnit guys had this approach, and they kind of looked at the other world. You know the dark side I'm talking about, right? C#. And they have NUnit. And the NUnit guys said, hey, we have attributes long before Java had annotations. And so they used attributes to build a concise test. But the NUnit guys are very smart. They wrote this approach and they waited. And they waited until the JUnit guys picked it up. As soon as JUnit picked it up, they went and deprecated on the NUnit side. And they said, this is terrible, don't do it. So these guys are stuck with it now, right? Very smart guys, right? Now, why is this such a terrible thing? The problem is, it looks concise, but I want to argue this is not concise code. This is terse code. Why is this terse? Why am I complaining about this? The reason is, a terse code is a code that appears concise, but is tricky. It doesn't do what you expect it to do. I don't want a test to ever pass for the wrong reason. I want a test to only pass for the right reasons and fail otherwise. But notice this particular test. If any of these two lines of code throws this exception, this test will pass. My intent is to make sure max profit throws the exception. But if the set price were to throw the exception for some reason, this test would end up passing. What do? Well, if you don't know a better way to solve it, go back and write this verbose code. It's much better. Or if you can use lambda expressions to solve it. This is a syntax from Java 8, by the way. In Java 8, you can write something like, you can say set price. If that fails, this test will fail. And assert throws, I want to make sure the max profit throws this particular exception. If the max profit doesn't throw any exception or throws some other exception, this test will fail. I would argue this code is concise, this code is terse. I don't want terse code, I want concise code. If I cannot have concise code, I would rather go have a verbose code which does the right thing. So don't confuse terse and concise. Terse code is not simple. Terse code misleads us a lot. So don't confuse terse with concise and simple. This is one of the quotes that I really like. Sir Tony Hurst talked about this. He said there are two ways of constructing a software design. One way is to make it so simple that there are obviously no deficiencies. And the other way is to make it so complicated that there are no obvious deficiencies. I was working on a project. I was asked to come and code review. As I was reviewing the code, this code was fairly complex, but I found out in the middle of this code, they were modifying a shared mutable variable, and they had not protected this variable at all. So I immediately called the team and said, guys, did you know that right here you have a violation of consistency, race condition on the thread? bad things can happen. As soon as I said it, one of the developers got very angry at me and said, hey, Venkat, this application has been in production for 3 years. What makes you think it can come and scare us right now? And before I could answer, another developer said, yeah, but every 3 weeks it'll crash and we don't know why. Could this be related? Right? So it could be so complex we don't even have a clue why it is, is it even working? Is it even correct? Well, okay, you told us what's not simple mostly. Well, we came here to know what is simple. Can you tell us about what is simple? Simple keeps you focused. Simple keeps you focused. Code that is simple keeps you focused. Code that is not simple, what does it do? It wants you to take a coffee break. It wants you to go find a quiet room and cry for a few minutes and come back to work. Right? You go to the corner and say, God, why did you create code like this? God, why did you create people who create code like this? Right? It takes focus from what you're doing. Let's say for a minute, let's think about this with a different example than code. Let's say for a minute, I'm working on something and I want to make a function call to make a certain operation, and I quite cannot remember what this function is, and my IDE doesn't help me right now. What should I do, by the way? Search. Okay, let me search. What am I searching for? I want to search for prototypal inheritance. Yeah, that's a great idea. Somebody said prototypal inheritance, I want to search for it. Let me go search. Can I search? Yeah, why not? Where do I go to search? Let me search in Yahoo if you don't mind. Because Yahoo is a search engine, right? So search Yahoo. Hey Yahoo, I want to type prototypal inheritance. Let's do it. So I want to ask Yahoo, what is prototypal inheritance? There. Oh, wait. Whoa. High school student takes model. Did you know that? These high school students are getting really smart these days. Oh, wait. Fast and Furious. Have you seen that movie, by the way? No. They tell me it's an incredibly good movie. Oh, colleges are oh, I knew this already. Colleges are definitely a ripoff. What else is there? Oh, there's a scam. Interesting stuff. Samsung, interesting. Cell phone, ooh. Wait, what are we trying to do, by the way? Search, oh, thank you for reminding me. Search prototypal inheritance. Let's try a different search engine. Bing. Hey, Bing, I want to search. All right, search for prototypal inheritance. All right. Wow, look at that picture. Does anybody know what this picture is? I want to go there. I want a vacation over there. In fact, that reminds me, I got to book my vacation. But I'm really scared to search for whom to go reserve vacation with, because I may be in a recursive pattern now, right? Oh, try Google, he says. Let me try Google. I want to search Google, what is prototypal inheritance? Come on. Prototypal. What happened, by the way? Can you imagine this? It gave me that. And what is there to see? Nothing. Can you imagine this? The first day, this developer went to his boss and said, I'm done. What do you mean you're done? Here, I see a text box. I'm done. Don't you think this is pure courage? It is pure courage, isn't it? Oh, here's a text box. What else? There's nothing else. Go home. This is for people to search stuff. Oh, okay, you really insisted I put an I feel lucky button over there. This keeps focus. Well, there's enormous complexity behind this, right? But it keeps you focused. It is not taking away your focus from anything, right? What are you there to do? Search. Then search. Don't read about other stuff. Hey, I really want to know what high school students are doing these days. Well, then search for that. Don't give me crap when I'm trying to look for stuff that is important to me. Keep my focus. Don't distract me. Simple things keep your focus. That is very critical. Because if you lose your focus, you lose your productivity. So don't go to sites. That's the reason I use Google all the time. And of course, I go to other sites when I really want something else, not search results, right? So yes, the complexity is there behind it, but they didn't push that complexity to you. They didn't distract you from getting your work done. And they said, you are here for one purpose, and we're going to get that done for you. And there was a time, by the way, a year ago, maybe, can't remember exactly when, Google started putting pictures on the page, and there was a hue and cry from people. And I hated that too, because all of a sudden I go to search, and I'm waiting for my slow network to respond, loading a stupid image that I don't care about, right? So this is a wonderful quote. Perfection is achieved not when there is nothing more to add, but when there is nothing left to remove. What a great way of thinking. We call this refactoring, don't we? And what is the refactoring I do mostly? I go in and remove complexities, remove code. Hey, we don't need that. We don't need this. So let's not confuse. Let's not take attention away from what we're doing. Simple eliminates accidental complexity and hides inherent complexity. Simple takes away accidental complexity. You go in there and do stuff that is not material. It doesn't take away it takes away those things from you and hides the inherent complexity. So as a user, as a reader of code, you're not bothered by things and you're able to easily understand and cope with it. If your solution is more complex than the problem, why solve it? Right? That's important. Okay. Simple fails less. Simple fails less. How can it fail less? Well, you want to have fewer moving parts. It fails less when you have fewer moving parts. What fails more? When things constantly change. I'm reminded of this experience. I was writing a piece of code one day. I actually had a guy approach me, and he had a function. And the function he had, some function, and this function took a parameter as a value, and deep down in this code, right, somewhere, it was not even a very long method, and right in the middle, a equals 22. And then he goes on to write more things, right? And he came to me. It was his code. He came to me and he said, hey, I have this code, and it's not working. Can you help me fix it? I am reading his code. And I tell him, you know what? This code seems to be doing what it's supposed to do. Yeah, that's the problem, but it's not right. It's not giving the right result. So we both are sitting and scratching our head. Eventually, I came to the line where this variable is being modified. And as I'm stepping through the code, I'm like, oh, wait a minute. Are you changing the parameter you got? And he's like, yeah, that's a bad thing, isn't it? It is a terrible thing. It should be crime punishable under law, right? It becomes hard to understand this code. Things break. Simple code. So what is this recommendation in Java? We say in Java, start with final, right? Don't change your parameters when you receive it. What if a language prevents you from doing it? Like in Scala, all your parameters are final. You cannot change your parameters in functions you write. So it fails less. Immutability leads to code that fails less. Why is that, by the way? And the reason is there are fewer moving parts again. It fails less. Why is the manhole round in shape? Anybody knows? Oh, it won't fail. Or you expect a runtime exception from it, or what? It doesn't fall into the hole. It doesn't fall into the hole. By the way, if you're trying this, don't tell me I asked you to try it. But if you go to the manhole and try to take this and try to put it inside, it won't fall inside. That's only part of the reason, by the way. That's half the reason. The half the reason is it won't fall in. Who wants to be the worker who says, whoops, all right, Johnny, go get it. Right? It doesn't fall in. But that's not only reason. That's half the reason. If you Google for this, by the way, you would be surprised at number of shapes that do not fall in. Trust me, there are several. But the problem with a lot of those shapes is you would bring it and say, all right, how do I fit this now? And you got to sit there and say, will it go this way? Will it go that way? Will it go this way? In the meantime, somebody's going, are you done? Can we go home now? But the beauty of this is there is only one way it works. Hey, how do I put it? Put the damn thing, let's go. Right? There's no other ways to do this. It just works. And you can see that there are various other fancy shapes people have created and say, look at this shape. It will never fall in. But how do I put this in? Well, you need a PhD to figure this out. Sorry. So that's the two advantages of this. It's very simple. It only works one way, and it doesn't fall. Simple's easier to understand and work with. It's easier to understand, and it's easier to work with. Let's think about this for a minute. I want to find a prime number. So what is a prime number? Oh, we know what a prime number is. It is a number that is divisible by 1 and itself. Great. How do I write a prime number? Well, we know the familiar way to do this, right? The familiar way to do this is to write a for loop. Great, we can do that. And in that, of course, mutate, go through the loop, and if there's a value that's divisible, return a false, otherwise come out and return a true. Or we could do something like this. This is very unfamiliar. What does it do? Stream.intRange. I want a range of numbers from 2 to the square root of the number. And then I'm going to say none of these match a divisor. So I've not written a for loop like I normally do, but I use the functional style in this case to compose this. Very unfamiliar. But is it simple or complex? Well, it certainly is unfamiliar, but once you get familiar with it, how hard is it to read it? Oh, I know what a stream.intRange does. It gives me a range of numbers. Given this range of numbers, tell me that nothing matches that range. Huh. That's what it does. It reads as it is supposed to in the problem statement. But we have to be familiar for that, right? If you're unfamiliar, it's hard. Give me a range of numbers, and in the range, none matches divisible by. Oh. Okay. Let's look at this example. Primes, given a starting point, if the number is a prime, then concatenate that number with all the primes that follow. Otherwise, just give me all the primes that follow. How cool is that code? It gives you all the prime numbers, and you're thinking, this speaker has gone mad. He's gone crazy, right? This will never work. Why not? Because you cannot create an infinite collection like this. You'll get a Stack Overflow before anything happens in Java. But what if infinite collections are available? So during the holidays, by the way, I wanted to write a book on Java 8 lambda expressions. Because Java 8 is going to introduce lambda expressions, I thought this would be so cool to write a book on the topic. And I said, how would I do this, right? And so I was experimenting with a lot of different things, and I wanted to implement a way to implement this particular thing. And I discovered that Java 8 has actually lazy collections. How cool is that? So notice what I did here. Very unfamiliar, because this is not even released yet. But what does it do? Next prime, it takes a number. If the number is a prime, return number plus 1. If it's a prime, return the number plus 1, because I want the next prime. Otherwise, just ask the next prime to give me another number following it. Okay, that's simple. Primes, starting and count. What does it do? Streams.iterate, next prime starting, sample, : next prime. Hey, what in the world is that? It's an infinite series of numbers. But how could you ever create an infinite series? What if the infinite series doesn't create it when you ask for it, but only when you demand the result? It postpones execution, lazy infinite collection. So it says, I'll start here. Here's how I know to generate the next number, but I won't do anything right now. Okay, that's cool. And then limit count. Only give me that many numbers. And then put it in a collection and return to me. Now, when I run this code, by the way, I say, give me prime starting at 0, if it's prime, of course, or the next one, and give me first 5 primes. That's the first 5 primes it gave me. And I say, start at 100 and give me 7 primes. That's 100 primes from that. That is the entire code, by the way. There's no additional code except for imports. Simple is elegant. Simple is beautiful. Simple pleases you. Simple makes you happy more than complexity does, if you get a hang of it. This is the most popular painting in the world. Isn't that surprising? It is so simple. It is so pleasing. You can keep looking at the painting. Sure, there's a lot of complexity under that. We want to say it's complex because it's a masterpiece. It's got to be complex, right? But should it be? This is an extremely simple painting. What does it have? It's got a lady. I mean, I'm not saying ladies are not worth looking at. We all do. But nothing that we have not seen. And yet we say, oh my goodness, what a masterpiece. But there is something else for us to think about. This could be very cluttered and complex. But it's not. It is simple and so elegant. There's a story of a building in Boston. In Boston, there was a building. Jan Hancock, a big company, wanted to build a building in downtown Boston. They applied for a city permit, and they were told, no, you cannot build here. Obviously, you cannot build here. Why not? Because if you build a building next to this beautiful, beautiful church, you will spoil the look of the church. So no, we cannot give you permission to build it. Well, you have a building to build. What would you do? We can bribe. Some people do that, but I don't like that. The architect of this building came with a marvelous idea. He said, no, we want to build a building here. And when we build it, the beauty of this church is going to increase. No, you cannot touch the church. No, we're not going to touch the church. And when I walked through Boston, by the way, I was captivated by this building. Not this building, but that building that I'm talking about. Why? Because the architect did something marvelous. He said, I'm going to put a reflective glass. It is so beautiful to look at the church reflection on this building, by the way. What a simple, elegant solution to solve the problem. And you can go there and you can look at the church and look at this building, and it is captivating. Cameras don't capture this as much as I enjoyed being there. I just stood there for several minutes. I just couldn't move. It was that beautiful. However, we need to keep in mind, simple has to evolve. Do you think that the greatest of the minds in history, who did those marvelous paintings and sculptures, sat there and said, I'm the expert, and I'm going to draw this painting. I'm done, guys, come and take it. Did they do that? Definitely not. History has shown that the best of the minds we have had in our history, those who created masterpieces, created several prototypes. History shows that you're looking at a masterpiece, but there are paintings where there's this lady with a hand on this side. There's a painting with her looking this way, and then the masterpiece in one certain way. And you say, look, all these are the same painting, prototypes until they evolved. The greatest of minds, by the way, did prototypes. And we come to work every morning and say, I'm going to write code now, and I'm done. I want it to work now. In the meantime, the boss is like, are you done yet? How silly it is that we want to sit down and write code once and be done with it. Software has to be not written, it's got to be rewritten. It's got to be evolved, it's got to be refactored. And that's when we can arrive simplicity and improve quality. We cannot just do it in one sitting. It's impossible to achieve that. It is naive to think that we can do it. In fact, it's kind of irony, right? We refer to construction business and we say, look at what the engineers do. Well, I'll tell you what the engineers are desperately doing today. The engineers are desperately saying, you know what, when we come up with a bright idea, it takes us 6 months to see a prototype of it. That sucks. So thank God for 3D printers. We are able to see this prototype and see how it works in 3 days. That's what the hardware guys are doing today, by the way. He's trying to create prototypes. And yet, the word soft in software simply says we can create prototype after prototype after prototype any number of times. And yet, in our field, we don't want to do it. How sad that is. We fear creating software. I better get this right. Why? Make mistakes. What is going to happen? I was talking to a developer. I don't want to do it. I said, why not? What if it breaks? I said, I guarantee you, nobody is going to die today because of the code you're writing. It is just on your machine. Let's experiment. Let's try. Let's see what it does. The only thing that can happen is we can learn from this experience, and then we can go and build it. So we have to evolve code towards simplicity. Richard Feynman said, if you cannot explain something to a first-year student or a 6-year-old child, then you haven't really understood it. This I find a lot of times, by the way. We are not able to do things because we think we understand, but we really haven't understood. It takes a lot of time and effort to understand things. By the way, understanding things, learning is like peeling an onion. You peel a layer of onion, what is there now? More layers of onion, right? You keep peel layer. And by the way, what happens when you peel an onion? You're crying, that's correct. Learning is like that. If it doesn't involve crying, you're not peeling the right onion. It should be a little frustrating. Why? Because what you learn should fundamentally change the way you think. If what we learn doesn't alter our behavior for good, there's no point learning it. That's what learning is all about, right? So we can get better and do something different and better. And if it doesn't change the way we do things, why learn it? And a lot of times we don't explain things properly because we don't understand it. I have been teaching C++ for several years, by the way. And one day I was trying to explain something in the class, and everybody looked at me and said, we don't get it. I said, what do you don't get it? Come on. No, we don't get it. I said, okay, I'll come back tomorrow and explain it. I went home. Why is it so hard to explain? And suddenly I realized, after teaching this for several years, I have not understood it. I thought I understood it. Then I spent the entire night researching and reading and experimenting and playing with it. And suddenly I'm like, oh my God, how did I not know this so long? It opened up a door. It's another layer of onion peeled. The next day I came and explained. Within 5 minutes they're like, oh, this is simple. Why did you have so much trouble explaining it yesterday? I said, because I didn't understand yesterday. Just now I understood, thanks you guys, right? If you have two equally likely solutions to a problem, choose the simplest, says Occam's razor. So anytime you have multiple solutions to a problem, choose the simplest solution, not the most complex. It is important to choose simplicity. I was writing a book on Java 8 during the break. And I came into Java 8 and I said, what can I do in Java that I know I can do in other languages? I know Scala, I know Groovy, I've played with this so long. I'm eager to see what Java can do with all the things that Scala and Groovy and Clojure can do. I was eager to find this out. And I said, I know how tail call optimization works in Scala. I know how tail call optimization works in Groovy. I know how tail call optimization works in Clojure. Can I do this in Java? Well, the first answer is Java doesn't do that. And I said, it would be so cool if I can find out how to do this in Java. So I experimented. And during the holidays I was writing the book, I said, I'm going to spend time just trying something out. And you know what? This took me more than 12 hours. The entire day I did nothing, just work on tail call optimization. And at the end of the day, I had a solution. And of course, I was proud. This is working. And I said, I'll put this away, I'll come back after a week and I will write about this. And a week goes by. The morning I start writing about it. I spent 2 hours. I could not write about it. That's when I realized I have created a monster. I cannot even explain it. The explanation I could give was, tough luck. And I realized, you know what, this is not going to help. I cannot write a book on this. This is so complex. So what did I do? I forget about writing the chapter. I started refactoring the code. And after refactoring the code, I ended up with something that was kind of reasonable. Let me show you what I have. So here is a factorial. If number is 1, return number, otherwise return number times factorial number minus 1. Well, that's cool. But what happens if you try a large number? You get a Stack Overflow exception, right? Whoops. The recursion fails. Hey, tail call optimization is cool. There's this fantastic book called Structure and Interpretation of Computer Programs, and they talk about how to implement tail call optimization to get really good behavior in code and get really implementation of recursion. this has been implemented in different languages. How can I do this in Java? So I set out to do this. So what did I write? I wrote factorial. It returns a tail call object. See that? If number is 1, return done fact, otherwise return call to factorial. Hey, that's kind of not a lot of code. I can understand this if I'm familiar with this. But the complexity is not in this code. The complexity is how do I implement tail call? So I did. After 10 hours of refactoring effort, right? The 12 hours is gone. After 10 more hours of refactoring, I got this. What does this do? Tail call is an interface over here, a class tail calls. It really has a call method, which simply returns next call. What does done do? Done says, I got anonymous inner class here. If it's complete, then return true. A result returns value. Well, a bunch of stuff related to Java 8. I don't expect you to know this right now, but don't worry about it. That's not where I want to go. This is the entire code, by the way. What does this code do? Well, I got a tail call. I got an apply method. The crux of that is in the invoke method. What am I doing in the invoke method? In the invoke method, I say, are you complete? If you're not complete, keep moving on to the next tail call until you are complete. Very simple, right? So keep working until the call is complete. I wrote this. This, by the way, is the code after 10 hours of refactoring, after the 12 hours of experimentation. You can imagine what I had first. It was a 30, 40 lines monster. And I refactored this and I said, wow, this is small. But once I finished it, there was a small problem in this code. Do you know what the problem is in this code? What is happening here? Mutability, right? Mutability. Remember I told you, no moving parts. And it was so funny, by the way. As I was writing this, until that page in the book, I kept telling, don't use mutability, don't use mutability. Now I'm using mutability. So I wrote, don't use mutability except when you cannot. That is so silly, right? I wrote this and I said, I don't like this. And I didn't know how to fix it. And then I kind of put this in the back burner, went on to do stuff, and I realized my code simply sucks. I was very unhappy with my code. Then I was on the treadmill. By the way, a best place to solve problems is to detach yourselves from the problem. Most of the time this works. You're sitting there and banging your head against the wall. I don't get it. Just get up and walk away. Get a cup of coffee. Look at the world outside. Look at the birds chirping. And then you come back and you solve the problem. I was on the treadmill. By the way, being on the treadmill is the worst time of the day. I don't know if you've noticed this. The time is really interesting. You're having fun. And you get on the treadmill and the time slows down. Have you seen this? And you're like, oh, when will this be over? So treadmill is the worst time of the day for me. But I have to, otherwise I get sick. And so what do I do these days? I get on the treadmill and I think about fun things like coding. So I was thinking, how do I solve the stupid problem of mutability? And I was shocked. There was a solution I had not even thought about. Rather than using this mutation, what if I take this tail calls and take each of the tail calls, and if you think about these as an infinite collection of tail calls, what an interesting way to think about it. If they are infinite collection of tail calls, keep solving them until you get to a call which is done. And the minute I thought about it, I jumped out of the treadmill, ran over to my computer and said, this is interesting, I've never thought of this. And so I wrote this. I said, get me an infinite collection of this object, starting here, and you keep generating the apply method until you collect the one that is complete, and I want the first one that completes, by the way, and get the result. Again, you have to be familiar with Java 8 to know what this means. But once you get a hang of it, if you've done Clojure, if you've done Scala, you know infinite collections. And the minute you know infinite collections, you're like, oh, execute an infinite collection and get me the first element. By the way, Java does lazy evaluation of functions. These functions don't execute like you see them. It executes them lazily. And once I wrote this, I was shocked. It actually worked. Has it ever happened to you? Absolutely, right? You write a code and your heartbeat is going up. Will this work? And then you see the code working and you just sit there and stare at it. You're in tune with your code at this moment. Rest of the world kind of revolves around you. You know the feeling, right? And you're like, wow. And there's music playing in your ears, but nothing happening around you, right? It was that one of those moments. And I realized I was able to solve this problem with no mutability in. But then I asked myself, hey, this is simple, I would say. And then a few minutes later, I would say, but is it simple? So Einstein says everything should be made simple as possible, but not any simpler. How do you know? That's my problem. How do you know that it is simple, or is it can be more simpler? Or is it adequate? Is it enough? How do you know this? How do you get to that point? So is my code simple? Or can it be simpler? Or is it something that should be more simpler? How do I know? So now you know my dilemma. I'm going to say my code here is both simple and complex. This reminds of something we started talking about, isn't it? Simplicity sometimes feels like Schrodinger's cat. It can be simple and complex at the same time. It depends on who is looking at it. Depends on whether they are comfortable with it. For people who share the context, is it simple? This is one of the reasons I would say ask people to do code reviews for you. Let them tell you whether it's simple or complex and evolve it from there. We can learn from each other and do it. But creating simple code is more instinctive. It is a sense we develop. How do you feel? And simplicity often comes from that feeling we develop. Some people call it experience, but experience is not the number of years we work, but how do we respond? How do we identify things? You go to somebody who is really good at something, you say, what do you think? They blurt out, I don't like it, or I like it. Then you say, why? Now they begin to think. Let me think about why I like it. Or let me think about why I don't like it. Because it's very instinctive. Simple makes things easy, but certainly it's not easy to create simple things. It is a lot of hard work to create simple things. And we only get better at it by doing it, not otherwise. As Da Vinci said, really aptly, simplicity is the ultimate sophistication in life. It's a lot of fun when we get a hang of it. Let's go create something wonderful, simple, and marvelous. Thank you.